So now here we are at 6.5b, and we're still going to focus on the 6 main trig functions. They're reminding you that the x is in radian measure. You have to do it in radian measure because it's a real number. And y represents the trig value, or the amplitude or height. And so what they're reminding us of is, and I'm not sure why he didn't show you this a long time ago, this is for the sine. So remember, this is x, which is in radians, and sine of x, or y. So if I come in here and we just write, this is the sine x. So sine of 0 is 0. Sine of pi over 6 is 1/2. Sine of pi over 3, I'm not sure why you put 0.87 because everything has been exact. Root 3 over 2. Sine of pi over 2, 1. And then look, it follows. Root 3 over 2, 1/2, 0. Right? And then goes negative, negative 1/2, negative root 3 over 2. And you get those cycles. So if you graph that, you get a nice smooth curve. And this is what it looks like, right? This is the pi over 6. This is exactly what you saw on this 6.5a graph. Now notice it goes on forever, but this is the graph of one period of it. To obtain other points on the graph, you just select other values, but you know it's repetitious. And so all you're getting is something just like this. This was if I go and make it really huge, this right here, I'll just highlight it. This is what we were graphing in 6.5a and in that first part. But truly, let me highlight that a little bit better with the highlighter. This is the part that we were graphing in 6.5a, but we know it goes on forever. That's what we call one period of it, because what happens after that period is that it cycles after itself. And that's what actually why sine's very, very useful to use. And cosine for wave types of things. It's periodic. The domain is all real numbers. There's no limit to what you can take the sine of. But the range, it's only going to spit out values between 1 and -1 because of its periodicity. You can see that it has a period of 2 pi and that it's going to have x-intercepts. Let me get rid of this thing. It's going to have x-intercepts at all the multiples of pi, whether they're positive or negative multiple. It's going to have y-intercept, or a maximum value, at the pi over 2 reference angles, and a minimum value at -1 occurring at these pi over 2 reference angles. And so a lot of information right there. They do mention that sine's an odd function. Odd functions are symmetric about the origin. That should make sense from earlier in this class. I think you did even in odd functions, and we are totally symmetric about that origin. So he's just relating everything back to stuff that you've already done. The easiest way to think of one period of a trigonometric function is to ask, what is the smallest part of the graph that could be used to stamp or create the entire graph? So he's just picking something arbitrary here. He could use that to stamp the rest of the graph. And so if you had that picture right there, remember that went from 0 to 2 pi, and you kept stamping that, that would be one period. So that's why we say the period is 2 pi. I think in most of his homework examples, he's asking you to graph just one period of the function. Some books will ask you to do 2. One period is from 0 to 2 pi, yeah, and that's what we're looking at. And so we're just harping on that sine function. Cosine function, pretty much the same thing. We have memorized 0, cosine of pi over 6. Oh, big mistakes, right? This is absolutely wrong. This is super sad, because if you're looking at this, and then looking at this, you're wondering, why am I not going through the point 0, 0? That's because this isn't the cosine. Let's go in and put in the cosine values and fix this problem. Super sad. Okay, so we're going to come in here. Y is now cosine. So he copied this, but he didn't change anything. The cosine of 0 is 1. The cosine of pi over 6 is root 3 over 2, but I'll put as 0.87. The cosine of pi over 3 is 1/2. It's falling. The cosine of pi over 2 is 0. And you can see that happening here. 2 pi over 3, and you're going right back up. 2 pi over 3, and it's cosine, so it's going to be negative 1/2. 5 pi over 6, still in that second quadrant, root 3 over 2. Pi is going to be a -1. 7 pi over 6, negative root 3 over 2, then a negative 1/2, and you're coming right back to 0 at the 3 pi over 2 mechanism. And you can see that that's being modeled here as well. So super sad that he had those incorrect, but glad that we were doing this video. And so you can see those points there. Now that graph makes sense. That's one period of it. And so to obtain the other ones, you would just plug in other values, and you recognize that it's very repetitive. And so properties of the cosine function, its domain is also the set of real numbers. Its range is also from -1 to 1. Its period is also 2 pi. But the difference is where what it is. It's actually an even function. Remember what even functions are. They're symmetric about the y-axis, and if you flip this thing over the y-axis, they would be right on top of one another. It's nice that they're folding in those concepts that you learned with Professor Eitel earlier. The x-intercepts are all the pi over 2's. 3 pi over 2's, pi over 2's. The minimum value occurs, the maximum value occurs at all the even multiples of pi, and the minimum value occurs at all the odd multiples of pi. Just some things to observe in there. And so he goes over, I'm not sure why, but he goes over the period again, and it justifies that it's 2 pi again, but we've seen that. And then there's one period of it. And honestly, one period is very subjective. It absolutely, in fact, in most books, it'll look like this being one period from 0 to 2 pi. That is absolutely one period. You get a mix in there. If you go with his definition of one period, that it has to be the stamp, well, maybe that would have worked. But that's what his one period's going to be. That's what he's going to reflect in the back of the book. So tangent. Tangent is cosine over sine. So at pi over 2, tangent sine over cosine. It's x over y. So at pi over 2, it's undefined. At negative pi over 3, it is 1.7. At negative pi over 4, it's -1. And at 0, it's 0. And so what does that do when we put all these points in? That gives us this shape right here that you saw in the 6.5a video. And so we have this. Now remember, there's asymptotes. Let me put them in red here. There's asymptotes coming right here at every pi over 2. And so that's what he's mentioning here. We got the vertical asymptotes in at pi over 2, and then he draws it there. And so we can get other points, and basically this thing just repeats itself. Here's our original one right here. Let me highlight it in yellow. This was our original one, but it just gets repeated. Every multiple of pi over 2 is going to be an asymptote. Every 0 pi, every multiple of pi actually is a 0 for us. That's what he's going to say here. The domain is not all reals, right? We can't plug in any of pi over 2, so it's all the reals except multiples of pi over 2. The range is everything, though. The tangent function is periodic, but it repeats itself every pi. The distance between here and here is pi. Whoops, that's not so readable there. So let me undo that type of mark and then just illustrate in here that the distance from here to here is pi, and from here to here is pi. It repeats itself every pi. And then it talks about how it's an odd function. Makes sense, it's symmetric about the origin. And then it names the x-intercepts like we've done and the vertical asymptotes. And there's no maximum or minimum values. And so that's what it looks like. There's a single period of it. And that's what we got. Cotangent function, he also plots values, and we go through this a little bit quicker. We realize that multiples of pi are going to be our vertical asymptotes. And so you can see that every multiple of pi is a vertical asymptote, 0 pi, and all of that. And so the domain is all reals except these multiples of pi. Its range is from -infinity to infinity. It repeats itself again after every pi. The difference between 0 and pi right here is pi. So that is its period. And then it names its x-intercepts. And then several periods of it. Sorry about that. And so there's our cotangent. Cosecant function. So the cosecant function is the flip of the sine, and so think of, that is so wise that he put the sine x values in here. At 0, sine 0. And if we flip 0, we get undefined. We flip 1/2, we get 2. We flip 1, we get 1. We flip 1/2, we get 2. And so he's picking things that are easy to flip, because all we have to do is get the general pattern. And so you can see, though, that it's undefined every time sine 0. And so it's undefined at every multiple of pi. But the best way to get it, if you're going to graph a cosecant, just know it's related to sine, and the best way to get it is to draw your sine function in. I would recommend drawing it dashed, and then do these parabolas off of its mins and maxes. That's what's going on when you look at your cosecant, because it gets big and gets really, really big. Its minimum values are well, it has no values between 1 and -1, and so it has these crux values in there. It can go as big and as small as you want, and so that's one period of it right here. It's just like you saw in there, and so they're reminding you that it's 1 over sine x. And so we're naming the domain and range. When it comes to the exam, he's having you just graph them. Same in the homework. I looked at the homework to graph them, and in the homework, all you're doing, the 6-5 homework is not partitioned into A, B's, and C's. It's just a 6-5 homework. And so this is what we got here for the cosecant graph. That's all of it. What's in red is its actual graph. The black is just helping us get that way. And then that's what it looks like. And then there's one period of it. One period would be, it does have a period of 2 pi in order to get a full period in there. That stamp set would have to be everything in the red. Secant function, you know what you're going to do. Upsetting. This shouldn't be sine. This should be cosine of x. It's the flip of cosine. And so those are the right values for cosine. Cosine of 0 is 1, but he has that mistyped in there. And so what are we going to do? We're not going to do that. We're going to draw our basic cosine graph that we have memorized, and we're going to put humps off the top and the bottom. That's what we're going to do. And it's that easy. So no stress. We're just going to go in there and graph again, this should be cosine. We're going to graph that cosine function and put humps off of the top and bottom. So here's your regular cosine function all drawn out, and then these tops over bottoms. Every time cosine 0 is a vertical asymptote. And then he lists the properties of the secant function going through. And it's a 2 pi 1. I don't think that we need to do too much more other than this is a summary. So all that, this is basically a repeat, this page of 6.5a. And so 6.5b is showing us how they obtain those. So we'll see what's in C next.